So good evening, everyone. So I also would like to share with you my thank to the organizers for this nice meetup, and also would like to thank Emmanuel for giving such a nice introduction to the topic. It will really help me entering into what I'm going to discuss, which is this many-body physics with quantum simulators. So based on the second type of platform that Emmanuel discussed, which is arrays of individual atoms that we make interact by promoting them to a Rydberg state. All this is work done at the Institut Optique, which is on the campus of the Université Paris-Saclay. So technically speaking, we're not in Paris, we're 20 kilometers south of Paris, despite the Eiffel Tower, which is here. All right, so I will I will just introduce you to the team very briefly, just to show you the kind of effort that it takes in an academic group to tackle this kind of questions. So about half the group works on what I'm going to discuss, so led by Thierry, who's a permanent staff member in our group. And so we have several PhD students, so Pascal and Guillaume at the moment, a postdoc, Anna, and Daniel. And also very important to us, our collaboration with theorists really coming from the many-body physics world, not like us, because we are really AMO physicists. So we collaborate with Andreas Leuschli in Innsbruck and Hans-Peter Büchler in Stuttgart. And I will show you the various various role they had in our research as the talks go through. So I don't think I need to introduce more all this. I mean, Emmanuel gave a very nice overview about that. So essentially what we're doing is synthetic matter that we use for quantum technology. So here the idea once again is to use the control that the community gained over actually decades to control individual atoms and bring them together, control their interactions. And the goal is to implement many-body Hamiltonians. And very importantly, many-body Hamiltonians that are not necessarily idealization of a real-world situation. So it can be a purely mathematical Hamiltonian that a theoretical physicist could come up with, or that could be useful for optimization processes. For example, you may need some spin models that are actually unphysical, so to speak. So with that, on with these machines, what you can do is quantum simulations of many-body problems, apply those quantum simulations to the solving of optimization problems. You can also, those machines are able to generate quantum states that are useful for quantum metrologies because they have the right amount of entanglement, so to speak. So you may have an enhancement of precisions of quantum sensors, for example. And finally, obviously, if we have, let's say, very good control, it needs to be refined, but we can hopefully reach quantum computers, full-fledged quantum computers based on quantum gates. Okay, so here what I'm going to discuss mainly is quantum simulation of many-body problems, and just using a very specific platforms, which is arrays of atoms that we trapped in optical tweezers. So the idea of an optical tweezer is just a single laser beam that you focus onto a size of typically 1 micrometer. So in order to do that, you use a special type of optics, but that are not so difficult to build. And the size of the trap is about 1 micrometer. And there you can place one and only one atom in this trap made out of light. So typically a few milliwatts are enough to create a dipole trap of a millikelvin depth. This was actually pioneered by Philippe Grangier at the Institut Optique about 20 years ago now. And so the idea now is that you may want to arrange all these traps in order to build an elementary many-body system. So the atoms, when they are trapped in these tweezers, you can send a resonant light on them, the atoms fluoresce, and you collect the fluorescence onto a CCD camera. And therefore, you can image the atoms one by one in exactly the same way as Emmanuel has shown. So of course, if you want to have many of these traps now, what you want to do is to multiply the tweezers, and we do that by using a holographic technique. So the idea is to imprint a phase onto the laser beam that creates the tweezer. So this phase, you've got an example here, leads to, in the focal plane, the Fourier transform of the phase factor. So if you want a given geometry, you just need to calculate the phase that you need to imprint there. And so with that, we were able to to create arrays with large number of atoms. So large is not as large as in the case of Emmanuel, who can reach the more than 1,000, but it's actually still larger than many other systems. So it's a few hundred atoms that now can be controlled. So those images that you see here are single-shot fluorescence images. So you can see that you can prepare arrays of atoms. So in 1D, so this kind of the snake-like configuration, you can have two-dimension patterns. So for example, in this square array or this triangle array, up to, as I say, a few hundred atoms. No defects, so essentially it's defect-free. So there is a lot of technical detail that I sweep under the rug here, but I mean, that were critical. And actually, even in our group, we spend a lot of time optimizing how we create those arrays. We can create any arbitrary array. So this is an example of a pixelized version of a very well-known paintings, just to show that we can arrange them exactly the way we want. And we can even arrange them not only in 1D, 2D, but also in 3 dimensions. So you have to be a bit careful for those particular images. Those are average images so that you have the feeling that all the traps are filled at the same time. Typically, this is about 300 traps. Here it's about 120 traps. Okay, so what we have now is these arrays of atoms. The atoms are well enough separated. So typically the distance between the atoms is a few micrometers. And therefore, the atoms at this distance do not interact, but on the other hand, the platforms is addressable. So you can measure the state of each of the atoms in a single shot picture. So now if you want them to interact, that's where the Rydberg part comes in. So Rydberg atoms are just atoms that are promoted to highly excited states, so state with very high principal quantum number, in such a way that classically, if you want to think of it, the electrons is very far from the nucleus. And this classical picture gives you the important features of the Rydberg atoms, which are twofold. The first one is that they have very long lifetime, at least much longer than the typical lifetime in low-lying states, so typically several hundred microseconds. And second, they have very strong dipole matrix elements that scales with essentially the size of the atom, which is the square of the principal quantum number. So the consequence of that is that they will feature very long and very large dipole-dipole interactions. So kind of a number to remember is that if two Rydberg atoms are separated by about 10 micrometers, they interact with the strength of the interaction, which is in the megahertz range. So that places us immediately on a time scale for any dynamics driven by the interaction, which is sub-microseconds. Okay, and you see now why even 100 microseconds can be considered as a long lifetime, even though, of course, it's not infinite. Okay, so now if you just take two Rydberg atoms, they've got several ways to interact, and I will illustrate those two ways one after the other. So the first one is what is called the van der Waals interaction, which I will detail a bit more in a second, but essentially this is a diagonal shift of the fact that two atoms placed in the same Rydberg states will exhibit an interaction scaling like 1/R6. Or they can also, if you have two different Rydberg states, interact via what is called a resonant dipole interaction. So I will say a bit more later. But essentially, what is important is that those two kinds of interactions allows us to map the physics of an ensemble of interacting Rydberg atoms onto either the quantum Ising model, which is the sigma Z type of model, or the XY model, which is, so to speak, an exchange interaction. So essentially, it's a flip-flop interaction where the two spins will exchange their state driven by the interaction. Of course, those spin models, you encounter them in many different cases. Usually, they are introduced in the framework of quantum magnetism, but especially the XY model is also a model which is very popular if you want to describe transport properties, because, I mean, if you got an up excitation, it can move between sites driven by the interaction. And I will show you what we can do with that. Okay, so what I will try to illustrate in the next 15 to 20 minutes is two examples where we use the different kind of interaction I've just described to either explore quantum magnetism using the van der Waals interaction, or to build artificial topological matter using the second kind of interactions. And it will lead me to this effort that we also have at the Institut d'Optique with the startup Pascal, which shows how mature the platform now is. Okay, so let me start with the quantum magnetism. So this is work we've done with Andreas Löschli in Innsbruck, together with his student, Michael Schuler, Thomas Lang, and Alex Eberharter. And before I explain you what we've done with that, I need to show you how we do this mapping. So this is something which we start from a platform of an ensemble of atoms interacting by a Rydberg interaction. So it has nothing to do with electrons carrying spin in the metal leading to quantum magnetism. But I will show you how we do the mapping. So essentially, the idea now is that if you place two atoms in the very same Rydberg state, they will interact with a C6 over R6 interaction. It means that this doubly excited state, so NS corresponding to a given Rydberg state, will be shifted in energy by an amount which is the C6 over R6. And what makes Rydberg so special is the fact that the C6 coefficient scales very violently with the principal quantum number, so typically the 11th power. So this means essentially that you've got a knob by which you can tune or switch on or off the interactions. So now if I want to describe this diagonal shift here, what I will write is kind of an Hamiltonian, an effective Hamiltonian, which is an N1, N2, where N1 and N2 are the Rydberg occupation number times the C6 over R6 interaction. So unless the two N's are equal to 1, there is no interaction. So it means that the atoms only interact if both of them are in the Rydberg state. And this is exactly like a sigma Z type of term in terms of spin language. So now, if I want to excite the atoms from the ground state that we prepare them using all the techniques that AMO physics have developed over the years, we need lasers, and essentially we pile up two lasers, so it's a two-photon transition, starting from all the atoms all prepared in the very same internal state, coupling them with a laser to a very well-defined Rydberg state. And so now if I write, I do all my AMO physics right, I can ignore the details of the AMO platforms and do the mapping that the ground state is spin down, the Rydberg state is spin up, and those two states are just coupled in a coherent way by a Rabi frequency omega. And to prove that this is coherent, this is an example of a Rabi oscillation that we measure on a single atom, and where we see that we can transfer the population from down to up. So now, if I want to write the full Hamiltonian governing an ensemble of particles of atoms that may interact in the Rydberg state through a C6 over R6 interaction, van der Waals interaction, driven by the laser, then I end up with this kind of Hamiltonian, which are three parts. First, there is the Ising part, which is the NI-NJ that describes the interaction. So this is the spin-spin interaction, if you wish. I will have the driving from the ground to the upper state, which is the sigma X interaction, the Pauli matrices, with the strength omega. And finally, I have the detuning, so the mismatch in frequency between the laser and the transition, which looked at this diagonal term, delta times Ni. And essentially here, I have a model that maps onto an ensemble of spin 1/2 that are placed in a transverse and longitudinal magnetic field and interacting via the Ising interaction. Experimentally, we can vary the parameters, and essentially we can vary the strength of the interaction, of the strength of the coupling, in a way that allows us to explore the regime from fully independent atoms to fully interacting. Therefore, we can map and study the effect of the interactions in this way. Okay, so I will just illustrate that on a very recent experiment we've done, where we benchmark how good the platform is. So essentially, I just consider an array of atoms placed in a square geometry. So I have an ensemble of atoms, and all of them are initially prepared in spin down. So it will be the ground state of the atoms, if you wish. And I will adjust the parameters in the Hamiltonian in such a way that if I have one atom excited to a Rydberg state, so it becomes a blue atom here, I cannot excite any other atoms in a sphere of radius A. Oops, I don't know what happened here. In a sphere of radius A. And therefore, I choose the parameters in such a way that the quantum part and the interaction part are the same order. So this is called the Rydberg blockade, but it's not essential. So essentially what this means is that within A, the spacing, I can only have one excitation. So now if I ask myself, how many excitation can I put in the system at zero energy cost? The lowest, the largest number of excitation I can put as this staggered configuration. So essentially, as I only have interaction between nearest neighbor, so this is zero energy cost. But if I want to add an extra atom, it will cost me energy. Of course, I have two degenerate configurations, either this one or the other one. Okay, those are called Néel configurations. Okay, so now people have studied the phase diagram of this quantum Ising model. So as a function of the detuning of the laser, which is the longitudinal magnetic field, and the transverse magnetic field. And in a very sketchy way, you have this kind of configuration. So essentially two regions, so an anti-ferromagnetic region separated from a paramagnetic region by a quantum phase transition, which is a second order quantum phase transition in case of a square. I placed dates here because I find it very striking that it was looked at as early as 1970, but actually people are still working on the details of the phase diagram. And so you have, when you go beyond the nearest neighbor approximation, you got two recent papers that actually look at the details around the quantum transition line. Okay, so very importantly as well, this phase diagram has only been known through quantum Monte Carlo simulation. So essentially, the critical exponents have never been measured in 2 dimensions in this system. And so this is actually new that people now have the platforms to check all these numerical predictions. So now how are we going to do that? So we're going to walk through the phase diagram by varying dynamically the parameters of the quantum Ising model. So essentially we can vary the strength of the laser, so which is the transverse magnetic field, the strength of the longitudinal magnetic field, which is the detuning of the laser, and essentially move from the paramagnetic phase, essentially all the atoms in the ground state. We vary the parameters and we drive them through the quantum phase transition towards these anti-ferromagnetic regions. Okay, so let's do that. So there were some actually early works on this, but not necessarily very fully quantum, and including by us actually in 2D. So in 1D, Emmanuel did a lot of work, the group of Michel Lukin. In 2D, we did some work a few years ago, but it was not fully coherent, I would say, and now it's much more coherent, as I will illustrate now. So we start from a defect-free array of 10 by 10 traps. So this is the first image that we take, and indeed we do see all the atoms preparing their ground state. Now we vary the parameters, so essentially we vary the omega and the delta, and we, at the end of this, measure it exactly in the way illustrated by Emmanuel in his talk. We measure what is the final state. So we do a projective measurement, we image where the atoms are, and this is what we get. So as you can see, every other atom seems to be missing. And actually that's exactly what you want, because in our case, based on the detection technique we have, a dark side corresponds to an atom missing, missing first, but which has been excited to the Rydberg state. So essentially, this is exactly the staggered configuration we have. So spin down, spin up, spin down, spin up. So this is an example of an AL state, which works very well. So it's a perfect anti-ferromagnetic state ordering. Of course, it doesn't work all the time. It works with a few percent probability, depending on the size of the array. But still, this machine can produce perfect anti-ferromagnetic state. But what is interesting is to study how the system evolves during the dynamics and to benchmark against the best theory that we have available, exactly in the spirit of what Emmanuel discussed. So I'll just show you part of the benchmarking we've done. We're going to use a number, which is the order parameter for the antiferromagnet, which is called the staggered magnetization. So essentially, this array is a bipartite array. So you've got the spin-up array and the spin-down array. And essentially what we measure is the difference in occupation between those two lattice sites in the bipartite configuration. So this is the order parameter we will measure. And so essentially, as time goes on, we will stop at each step and we will measure what is the staggered magnetization as a function of time. And we do that for this 10 by 10 array. So of course, you've got those dots here, which corresponds to the experiment. So you see that indeed we grow the antiferromagnetic configuration as we move across the phase diagram. And now we compare that with the theory. And so it's the theory that includes all the imperfections that we have independently calibrated on the machine. So we know exactly what is the interaction energy between all the pairs. We know what is the strength of the lasers and so on. And we compare that to a calculation, which for 100 atoms has to be an approximate solution, right? And it's based on what is called matrix product state. Just to give you actually how challenging this is theoretically to do this calculation, the line that you see, each of the line corresponds for a 10 by 10 array corresponds to a calculation which takes 10 days on a cluster computer. So you see that already this machine now do challenge the theoretical description, the numerical description of the system. And also what you can see is that the machine is very well described by, so in a sense, it's benchmark against the theory, right? And so because it agrees fairly well with the theory. The thing which is important is to realize that if we had no imperfection, we would have these yellow curves. So indeed, the machine is still not perfect, but at least we've got a good understanding of what are the delimitations. And just the largest number of atoms we've been able to explore is 14 by 14 on this platform. And essentially, this is impossible to do any calculations on this for this system size with a reasonable accuracy. Okay, so just to summarize this part, what we've done is to implement the 2D Ising model on a square. In a sense, this is the first implementation, I would say. You always have to be careful when you say first, but of the quantum Ising model in 2 dimensions. And once again, I emphasize the fact that this is rather new, that this can only be done with those artificial systems, the synthetic systems, because in real materials, the Ising model is only an approximation of what is going on. So you've got planes of spins, but there you will always have coupling between them. So it's very hard to be really into the full 2D regime. And then what we can study with this, and we've already started, I mean, together with a group of Misha Lukin, so the people look at the quantum phase transition itself, can measure the critical exponent, and we're also exploring the frustrated geometries when you have triangles and competition between the geometry and the anti-ferromagnetic order. Okay, so the second thing I will show you is something which looks completely different from the study of quantum magnetism. So I will hardly use the images of spins, but I will show you that you can build also with this artificial and synthetic matter topological situations. And I will use here a second type of interaction that naturally occurs for 2 Rydberg atoms, and which is called the resonant dipole interaction. So this is now work that we do with Hans-Peter Büchler in Stuttgart, and it's still ongoing work. So this is again what I showed you. So we've explored the van der Waals interaction. Now we're going to explore the resonant dipole interaction. In order to do that, I go back to the internal structure of the rubidium atom that we use. So these were the state we were using so far. So ground state, Rydberg state. And now I'm going to forget completely the low-lying states. I'm just going to focus on 2 different Rydberg states, state S, state P. Both of them are coupled by a dipole matrix element, which is actually very strong. And therefore, it's very easy with a microwave to drive the Rabi frequency between those 2 states. So this is an example of a Rabi frequency on a single atom of an atom initially prepared in P, and that you drive to the state S. Okay, so now from the point of view of the interaction, what is going on? So let's take 2 of those atoms. Each of them is a 2-level atoms. And I look at the following situation. I can have one atom which is in state P, while the other one is in state S. And what the interaction is going to do now is going to induce a flip of the state of the atom, with the state P going to state S, while the second atom goes from S to P, and with the virtual exchange of a photon, if you wish, but the strength of the interaction is the d square over r cube interaction. So what we implement now is really this XY model. So it's a flip-flop interaction where the spin of each, or the state of each of the atom, is flipped as a function of time. So of course you can either describe that in terms of S and P, or in terms of spin 1/2 system if you do the mapping of S being down and P being up. So let's go in the lab, measure the spin exchange. So we just take 2 atoms separated by 30 micrometers, which is a huge distance on the atomic length scale, but still it's something we can control. And we prepare one atom in P, the other one in S, and we measure after some time of letting them interact, what is the state of the atom at the end of this oscillation. And what we do see is that indeed the state of the 2 atoms swap from one atom to the other one, in an anti-correlated way, as it should. So, and once again, I'm always very amazed by the fact that atoms so far away can interact, exchanging interaction over a microsecond time scale. Okay, so now this interaction is a dipole-dipole interaction, so it's an anisotropic interaction, and we can measure essentially the frequency, which is directly the C3 over R3, the frequency as a function of the angle with respect to an internuclear axis. And we do see indeed this kind of dipolar pattern in polar plot that we measured. So you have the theory in a line and we have the data on the theory. So it shows you that it works very well. But the thing which I would like you to realize is that there is this particular angle at nearly 55 degrees where the interaction is exactly 0. So this is a feature of the dipole interaction which I will use, and it will show you how we can make use of specific features of the interaction in order to implement particular situations. So now, of course, I can discuss everything I said in terms of the p state hopping from one atom to another one, but I can use now a different language, which is the language of my p excitation is like a particle which hops from one side to another side. So essentially, I go from this situation of two interacting atoms to the situation of a single particle hopping from one side to another one. And this is having in mind this new mapping that we can implement some models, and the one that we're going to discuss now is what is called the Su-Schrieffer-Heeger model, which was a model introduced in the 70s in order to understand the electronic properties in organic polymers, such as polyacetylene, and which is actually now considered under a different angle of an elementary model featuring topological properties. So I will not go fully into the details of this, referring to publication and literatures, but we'll try to give you the science features of what we've done. The first important thing is that in 2012, people had predicted that based on the topological properties of this model, you should be able to observe what is called a new kind of topological order, which is called a symmetry-protected topological phase in 1D. So that was proposed in 2012, and it was purely theoretical, but you see that it's not a while ago, it's just quite recent, this prediction. And until recently, there were no realization of that, and now Emmanuel has one, and we had one using our platforms. So how do we model this system? So we have this organic chain, which essentially corresponds to an alternance of strongly and weakly bound between atoms. So the elementary way to model this is just to go to the tie binding limit in the dimerized limit. So in a sense, you've got a strong and a weak link, and to see how we can implement this model in the lab. So important to the Su-Schrieffer-Heeger model is the existence of what is called a chiral or sublattice symmetry, different words, which tells you that if you have identified two subchains here, you should not have any interactions, any coupling within a subchain. If you have that, then you've got a symmetry of the single particle spectrum, which turns out to be symmetric with respect to zero, the zero energy. So you've got a plus and a minus. And this is only if this chiral symmetry holds. And so now you want to implement that in the lab. And so that's exactly where this idea of having excitation hopping from side to side is going to be nice, because this is exactly what we have here. The excitation can hop from spin chain B to spin chain A and vice versa with a different coupling. And we're going also to implement this chiral symmetry by using this feature of the resonant dipole interaction, which is that for a magic angle, the interaction is exactly zero. So now we just take two spin chains, two atomic chains, what you have here, and you place them exactly at these 55 degrees in such a way that you do not have any coupling within a subchain, but you do have coupling between them with the alternance of a weak and a strong bind, exactly as it is represented here. So you see that now the kind of control we've got on the interactions allows us to implement a model which has some salient properties. Okay, so I'm not going to give you too many details of what we've done here because it becomes a full talk in itself, but essentially we've been able, using microwave spectroscopy in this system, to check the single particle topological properties in this system. So essentially an important feature is the fact that if you are in a topological configuration, you should have what is called edge state. So essentially the excitation should stay localized on the edge of the chain. And this is the length of the chain labeled from 1 to 14. And we do see that for certain frequency of the microwave, we do see the localization of the stage on the edge. So once again, it's just a sanity check that everything works in the single particle ratio. Of course, now the real challenge is trying to understand the interplay between topology and interactions. And here as well, I will not give you too many details, but just show you why you can access the many-body regime in this situation. Essentially, now we use this language that the P excitation is like a single particle hopping from side to side. But now if you've got two of them nearby, because we are only experiencing using two-level atoms, a P excitation cannot hop onto a second P excitation, just because, second atom, just because you do not have any energy to go to. So essentially what this means that those P excitations have infinite on-site interactions. And actually in technical world, they are called hardcore bosons. So it's a very specific type of interaction, but it turns out that this is enough to observe this symmetry protected topological phase. And I should say that it was a surprise to us. This is not something that we had thought of doing. It turned out to be something coming out of the experiment. which already shows you that these platforms are mature enough to actually do discoveries in a sense. So how do you add the excitation one by one in the system? Well, once again, using the microwave, you can add more and more P excitation until you fill half the sites, and when they are there, you've reached the ground state of this interacting Su-Schrieffer-Heeger model, which is this first realization of the symmetry protected topological phase that was predicted in 2012. So once again, just showing that those platforms now enable us to do discoveries and to implement non-trivial situations. What we're working on at the moment is trying to extend that to 2 dimensions, obviously, and you need for that some kind of spin-orbit coupling, which I'm not going to detail. But that kind of brings me to the conclusion and to the outlook, which is hopefully you've already seen through the talk of Emmanuel, through my talk, that those neutral atom platforms seems now to be mature enough that you can envision industrial type of application. And so that's in this spirit that we have created at the Institut d'Optique this startup called Pascal, so a year and a half ago now, having in mind to target scientific computing, but also optimization problems in finance, in the industry, and having in the company as the software and the hardware part. So everything is based on a given platform, which is this Rydberg platform, which I just described. And by the way, if some of you are interested, I mean, the company is hiring physicists and engineers. And you can find some kind of a roadmap, which is at the same time a review of the field of quantum computing at the moment in this paper of Loïc Henriet, who is a senior theorist scientist in the company. So I will just flash one particular example of application that is really of industrial interest. So people have discussed the possibility of what is called smart charging of a fleet of electrical vehicles. So essentially, you have a number of electrical vehicles, a number of plugs, and what you want to do is, for example, to minimize the charging time of your entire fleet, knowing that some vehicles have to be useful all the time and so on. And you also want to minimize, for example, the number of charging stations. So what we are looking at, the company is looking at in collaboration with EDF, which is the French electricity supplier, so it's a big company, we're looking at how to map this particular type of problems onto a graph problem, which is called a max K-cut type of problem. And there is a paper on the archive very recently where they actually show you how you can map this problem of application onto a max cut, a graph problem. Why is it interesting? Because now that this is a graph problem, there is a link which was pointed first by the group of Michal Lukin and Hannes Pichler. There is a mapping of this graph problem onto an ensemble of interacting Rydberg atoms. And so essentially now the question is, now that you've got your graph problem, can you implement it on the Rydberg simulator, do some kind of manipulation along the lines of what I've described, and hopefully find a solution to your optimization? And so people have actually looked very, immediately, that's the first question, and Loïc together with, Loïc has looked at the kind of implementation you can hope for based on the imperfections of the machine as we have them now. Okay, and it's actually kind of a roadmap of how those platforms should improve as time goes on. Okay, so that's one example of what the company is looking at. There are others, but already this is a concrete example of what you can look at using this Rydberg simulator. And this is my final word. So with that, I would like to thank you for your attention.
Thank you very much, Antoine.